Something extraordinary just happened in space science. For the first time ever, a spacecraft orbiting another planet has helped map an interstellar object with 10 times more precision than Earth alone. This video uncovers how ESA used its Mars orbiter to track Comet 3I Atlas, why this breakthrough matters, and how it transforms our ability to understand and monitor fast-moving visitors from beyond our solar system. The most surprising part of this discovery is how a spacecraft orbiting Mars, originally designed to study the red planet's atmosphere, became the key to unlocking a far more precise trajectory for the interstellar comet 3I Atlas. When the comet was first spotted on July 1, 2025, astronomers relied entirely on Earth-based telescopes to estimate its motion. That provided a workable starting point, but Earth's single viewpoint limited how accurately scientists could predict the comet's future position. The challenge became more pronounced because 3I Atlas moves incredibly fast, reaching speeds of around 250,000 kilometers per hour as it zips through the solar system. With numbers that large, even tiny errors in early measurements could translate into millions of kilometers of uncertainty later on. The breakthrough came when ESA recognized that the Mars-orbiting ExoMars Trace Gas Orbiter, TGO, would soon be in a perfect position to observe the comet from a completely new angle. Between October 1st and 7th, 2025, the comet passed within approximately 29 million kilometers of Mars, much closer than it ever would be to Earth. This gave TGO a vantage point about 10 times nearer to the comet than Earth-based observatories at the same moment. Even more important was the geometry. Mars saw the comet from the side, rather than the nearly straight-line view from Earth. To capture the comet, engineers had to repurpose TGO's Cassis camera, which was designed to map the Martian surface in high resolution. Turning it toward deep space required new pointing strategies, accounting for the spacecraft's rapid orbit around Mars and the faintness of the comet against a dense star field. Despite these challenges, the instrument successfully gathered astrometric data, precise position measurements, from its unique viewpoint. Once combined with Earth-based observations, TGO's data allowed scientists to triangulate the comet's exact path with unprecedented accuracy, improving predictions by a factor of 10. This was far beyond what scientists had initially expected and marked the first time astrometric measurements from a non-Earth orbiting spacecraft were accepted into the Global Minor Planet Center database. This moment didn't just refine a single comet's orbit. It demonstrated that spacecraft across the solar system could become tools for tracking objects far beyond their original mission purpose. Mars had unexpectedly become an essential partner in studying an interstellar visitor. The improved orbit of 3I Atlas is groundbreaking not because the comet poses a risk. Its closest approach to Earth is still more than 1.8 astronomical units, or roughly 270 million kilometers, but because it highlights a new way to monitor objects that move quickly through our cosmic neighborhood. Up until now, nearly all trajectory calculations for fast-moving objects have come from Earth-based observatories or satellites in Earth orbit. While powerful, these systems share a major limitation. They all observe from essentially the same point in space. 3I Atlas created the perfect test case to explore a multi-point observation strategy. By combining measurements from Earth and Mars, researchers demonstrated that two distant viewpoints can shrink uncertainties dramatically. This is especially important for objects moving at extreme velocities, where small changes compound rapidly. When a comet or asteroid appears for the first time, early measurements dictate everything that follows: where telescopes should be pointed, what instruments should be prepared for, and whether follow-up observations are even possible. The use of TGO shows that spacecraft not originally designed for comet tracking can still contribute crucial data. This opens an entirely new category of observational tools. Mars orbiters, lunar platforms, probes near Jupiter, or even spacecraft en route to other destinations could all provide angular diversity, the geometric separation needed to refine trajectories of newly discovered objects. Instead of relying on Earth alone, the solar system becomes a network of vantage points. This multi-location capability becomes especially powerful when an object is difficult or impossible to view from Earth. For example, when a comet approaches from the direction of the Sun, Earth-based telescopes struggle due to solar glare. A spacecraft located elsewhere, Mars, Lagrange points, or beyond, could observe it clearly. The success with 3I Atlas proves that spacecraft throughout the solar system can serve as an extended detection web. Another important outcome is the improved ability to study interstellar visitors scientifically. These objects enter our solar system only once and leave forever. Any lost opportunity cannot be recreated. With better orbital predictions, observatories can plan exact times to capture spectra, monitor activity, or study outgassing. For 3I Atlas, this meant guiding telescopes to observe the comet after its closest approach to the Sun, when its brightening activity reveals details about its composition. The Mars-based data ensured no observation window was wasted. This shift marks a new era of planetary awareness, one where the solar system acts as a coordinated observing array. The lesson is simple but transformative. With multiple eyes across different worlds, we sharpen our vision of everything moving through space. The refinement of 3I Atlas's orbit did not end with Mars. ESA's next step is to collect additional observations from the Jupiter Icy Moons Explorer, known as JUICE. Although this spacecraft is farther from the comet than TGO was, its timing is ideal. JUICE observes the comet shortly after its closest approach to the Sun, when outgassing and activity increase. This period reveals essential clues about its composition, structure, and behavior. Observations scheduled for late 2025 and early 2026 will allow scientists to monitor how the comet changes as it recedes from the inner solar system. JUICE's instruments can detect variations in brightness, shifts in its tail, or differences in reflected light that suggest evolving surface materials. The data will not arrive immediately. Transmission cycles and mission priorities mean results are expected no earlier than February 2026. But they will add another layer of insight to what Mars and Earth have already captured. Beyond JUICE, ESA is preparing several missions shaped directly by the lessons learned from 3I Atlas. One of the most important is the NEOMIR mission, designed to observe regions of space that Earth cannot see due to the Sun's overwhelming brightness. Many objects approach from the sun-facing direction, making them invisible to ground telescopes until they are extremely close. NEOMIR will sit between Earth and the Sun, detecting objects weeks earlier than Earth-based systems can. The success with Mars-based triangulation reinforces the importance of having multiple observation points. NEOMIR adds an essential one. Another mission influenced by this moment is Comet Interceptor. This ambitious project plans to wait in space for a still undiscovered comet, or possibly another interstellar visitor, then deploy multiple probes to study it up close. The improved ability to predict interstellar object paths directly increases the likelihood of a successful interception. If a future visitor resembles 3I Atlas, scientists will know its path much earlier and with far greater accuracy, giving Comet Interceptor a real chance to reach it. What makes this era so exciting is how cross-functional every mission becomes. A spacecraft built for atmospheric analysis can suddenly track a comet from another star system. A probe meant for the Jupiter system can turn into an interstellar observer. A solar sentinel like NEOMIR will become a searchlight for objects entering from hidden directions. Each mission gains added purpose, collectively forming a planetary-scale observation network. All of these efforts move us toward a future where tracking interstellar objects becomes routine. The refinement of a single comet's orbit demonstrated a scalable strategy, one that transforms interplanetary spacecraft into powerful contributors to deep space science. The more missions we launch, the sharper our map of the cosmos becomes. If you enjoyed this video, don't forget to like, share, and subscribe. Thank you for watching. See you next time.